Welcome to the lesson on section 6.3, Volumes by Cylindrical Shells. In this lesson, you'll learn how to use integrals to calculate volumes of rotational solids by the cylindrical shells method. You should note that this is not a required AP topic. All volumes on the AP exam can be calculated using disks or washers. However, you may find that using the cylindrical shell method sometimes results in an integral that is easier to evaluate. In the method of cylindrical shells, instead of slicing the solid into disks or washers, we imagine the solid as infinite layers of hollow cylinders with the axis of rotation as their center. Suppose the height of this sample cylinder is h. The circumference of the circular base is 2 pi r. If we unravel this cylinder, we get a rectangle with h as one side and the other side as 2 pi r. The thickness of this rectangular piece is dx because the thickness of the piece when in cylindrical form is horizontal. That makes the volume of the rectangular prism 2 pi r times h dx. To sum up the volumes of an infinite number of these shells, we'll integrate 2 pi times radius times height of each cylindrical shell. In example 1, we'll find the volume of the solid formed by rotating the region bounded in the first quadrant by the graphs of y equals 2x squared minus x cubed and y equals 0 about the the y-axis. Here's the graph. Without a calculator, you can find that it intersects the line y equals 0 at x equals 0 and x equals 2. The cylindrical shells would wrap around the axis of rotation. Sketching a cylindrical shell away from this graph, the thickness of the shell is a horizontal measurement, so we're working with dx here. The top of the shell is always going to hit the blue graph. So what y equals at the top is 2x squared minus x cubed. The bottom of the shell will hit the x-axis, so y equals 0 at the bottom. The height of the shell is y top minus y bottom, or 2x squared minus x cubed minus 0. The radius of the shell is x. Then using 2 pi rh as the area of the face of each shell and dx as the thickness, we get 2 pi times the integral from x equals 0 to x equals 2 of our radius x times our height 2x squared minus x cubed dx. To form the shells, imagine plugging in every radius from 0 to 2. The 0 represents the shell closest to the axis of rotation, and the 2 represents the shell furthest from the axis of rotation. In example 2, we'll find the volume of the solid formed by rotating the region under the graph of y equals x to the 5th for x between 0 and 1 and the y-axis. Again, since the cylinders wrap around the axis of rotation, our cylinders will stand up and the thickness runs horizontally to make this a dx. The top of each shell will hit the graph of y equals x to the 5th, and the bottom of each shell will hit the x-axis. The height of each shell, using y top minus y bottom, is x to the 5th minus 0, and the radius is x. Using the formula 2 pi rh, our volume will be 2 pi times the integral from x equals 0 to x equals 1 of radius x times height x to the 5th dx. Now let's look at an example comparing the disk method to the cylindrical shells method. Let's rotate the region under y equals cosine x squared from x equals 0 to square root of pi over 2 about the y-axis. To form disc-shaped slices, we slice through the axis of rotation. Here's a sample disc in the graph and outside the graph. The thickness is vertical, indicating a dy. The radius is what x equals on the right minus what x equals on the left, or square root of inverse cosine y. Since the area of a cross-section is pi times radius squared, the volume will be pi pi times the integral from y equals 0 to y equals 1 of the square root of arc cosine y squared dy. For now, you'll only be able to integrate this on a calculator. Now let's look at the same problem using the method of cylindrical shells. Each shell will wrap around the axis of rotation, and from my sample shell I can see that the thickness is horizontal, a dx. Since the height of the shell runs vertically, it can be found by subtracting what y equals at the top minus what y equals at the bottom, or cosine x squared minus 0. The radii will run through every x value in the region. Using 2 pi times radius times height, we find the volume to be 2 pi times the integral from x equals 0 to x equals square root of pi over 2 of x times cosine x squared dx. Unlike the disk method, the cylindrical shells method gives us something we do know how to integrate. Letting u equal x squared, I know that du equals 2x dx. If I take the 2 from the 2 pi that's outside the integral and put it back inside, I can match the 2x dx exactly. Converting our limits of integration, when x equals 0, u will be 0 squared, or 0. When x equals the square root of pi over 2, u will be pi over 2. Substituting, my integral becomes pi times the integral from u equals 0 to u equals pi over 2 of cosine u du. This is really pi times the sine of u evaluated from 0 to pi over 2. And that makes the volume pi. If we had to complete this problem without a calculator, we would choose to set this up using cylindrical shells because we can actually integrate this version. Now we'll look at the second part of the problem, revolving about the x-axis, first by the disk method. From a sample slice, I can see a horizontal thickness indicating dx. The radius of the slice will equal what y equals at the top minus what y equals at the bottom, or cosine x squared minus 0. Using pi times radius squared as the area of the cross-section, my volume is pi times the integral from x equals 0 to x equals square root of pi over 2 of cosine x squared squared dx. You don't know how to integrate this without a calculator yet, but you will after part 3 of this unit. Now let's revolve about the x-axis and find the volume by the cylindrical shell method. The shells will wrap around the axis of rotation, which is the x-axis here. The thickness runs vertically, so we'll be setting this up as a dy. The height of the cylinder is what x equals on the right minus what x equals on the left, or the square root of inverse cosine y minus 0. The radii of the shells will run through every y value in the region. And using 2 pi times radius times height, we get the volume to be 2 pi times the integral from y equals 0 to y equals 1 of y times the square root of inverse cosine of y dy. This again gives us something we don't know how to integrate without a calculator. So if we saw this problem again later in the year, we would choose to set this one up using disks if we had to do this again without a calculator, because we would eventually be able to integrate this one later on in the unit. In example 4, I'll find the volume of the solid formed by rotating the region under the graph of y equals x squared plus 2x plus 1 between x equals 0 and x equals 2 about the line x equals negative 1. my graph shows what the parabola would look like revolved about the line x equals -1, which is shown in bold blue. However, since we're looking at the region under the curve, as shown in yellow, the outside of our solid will actually be a cylinder with the line x equals 2 contained in the wall, shown by this thin blue line. So we're really finding the volume between that cylinder and the rid figure shown in the graph. A sample cylinder will wrap around the line x equals -1 and have thickness dx. The top of each cylinder will hit the red graph. So the heights are x squared plus 2x plus 1. If we were revolving about the y-axis, the radius of each cylinder would just be x. Since we're revolving about the line x equals -1, the radius of each shell will be x minus -1, or x plus 1. Using the formula 2 pi times radius times height, our integral will be 2 pi times the integral from x equals 0 to x equals 2 of x plus 1, which is our radius, times x squared plus 2x plus 1, which is our height. This concludes the lesson on section 6.3, volume by cylindrical shells.